Hey guys, welcome to another video. In this video, we are going to be talking about designing Chebyshev filters in digital signal processing. In our last video, we spoke about Butterworth filter design, and quite a lot of concepts are shared between both of these, at least till a point. So I suggest that if you haven't watched that video, watch that first, and then you can come back here and watch this. I'm going to be leaving the link to that video in the description box below. So let's get started. So what do we want? Again, just like in the case of a Butterworth filter, we need a transfer function h of s to successfully design a Chebyshev filter. Step 1 in the designing process is again involves the order of the filter n. Observe the change in this formula though. This looks pretty similar to that of the Butterworth filter formula, right? But look here. Instead of log, we have cos hyperbolic inverse, and rest almost everything is the same. Alpha s, alpha p, omega s, omega p, it all means the same as well. So alpha s is a stop band attenuation, alpha p is passband attenuation, omega p is passband frequency, and omega s is stop band frequency, right? What do we do with n? We round it off to the next higher integer. Deja vu, right? Now, this is the portion where we see a change. We need to find something we call the minor and major axis, denoted by the letter small a and small b respectively. So a, small a, is given by omega p into mu to the power 1 by n minus mu to the power minus 1 by n divided by 2. And small b, which is the major axis, is given by omega p, pardon me, into mu to the power 1 by n plus mu to the power minus 1 by n divided by 2. And what is mu? Mu is epsilon inverse plus root over epsilon square inverse plus 1, and epsilon, as was marked in the Butterworth filter video as well, is this value right here, root over 10 power zero point 0.1 alpha p minus 1. Chebyshev Chebyshev filter design is much more of a formula game as compared to Butterworth. So moving on. Then we have something we call the poles of a Chebyshev filter. The poles of a Chebyshev filter help us find the denominator of the transfer function. The denominator of the transfer function h of s, right? As we had discussed in the previous video, there's a numerator and there is the denominator. Similar to the Butterworth case, we first deal with the denominator in the Chebyshev filter as well, and then we go to the numerator. So the poles help us find the denominator of the transfer function of a Chebyshev filter. But there are some different formulae involved in this case. So the poles are given by Sk equal to A cos phi k plus Jp sin phi k. Now observe this. K goes from 1 to n, n being the filter's order, the order of a filter. Alright, this is the order of our filter. So if our order is 2, k is going to be 1 and 2. If it's 3, 1, 2, 3, 4, 1, 2, 3, 4. And those many cases we have to find S1, S2, S3, S4, phi 1, phi 2, phi 3, phi 4, and so on. Phi, which is here, is given to us by pi by 2 plus 2k minus 1 by 2n pi, where n is again the order of the filter and k goes from 1 to n. We use these poles, as I said earlier, to find the denominator of the transfer function. I know it's not making much of sense right now, this particular statement. It will get clearer the moment we get to the example case. Coming to the numerator value. Here, if n is odd, that is the order is odd, we substitute s is equal to 0 in the denominator polynomial, and that's what becomes our numerator. And here, if the order n is even, we substitute s is equal to 0 and divide it and divide it by root over 1 plus epsilon square, and that becomes our numerator. And therefore we have a complete transfer function h of s. Now moving to our example case, which will help us further understand how exactly do we design a Chebyshev filter. Given the specification, alpha p is equal to 3 decibels, alpha s is 17 decibels, fp is 1 kilohertz, and fs is 2 kilohertz. Determine the order of the filter and h of s. So this, even though the statement in this question says determine the order of the filter and HFS, it's basically telling us to design a Chebyshev filter, right? Because finding n and eventually getting HFS, which is the transfer function, is essentially designing the filter in itself. So this can be taken directly. Alpha p is 3 decibels, alpha s is 16 decibels. My bad, this is supposed to be 16 decibels. But see what's happening here. Let me change the color of the pen. We have something called fp here, and this is given to us in hertz. Similarly, fs, which is basically the stop band frequency, is given to us in hertz. But if you remember closely, in both Butterworth as well as Chebyshev, we need these values, these very values in radians per second, radians per second. So we do something, we do a simple conversion. Our omega p, which is omega p, which is basically fp in radians per second. We multiply the hertz value given in hertz with 2 pi, so we get 2000 pi radians per second. Similarly, omega s becomes 2 pi into 2000 hertz, that becomes 4000 pi radians per second. Simple conversion, but very important because it is easily overlooked, and if we directly substitute value in hertz, it will be wrong. The answer we shall get is going to be wrong. The entire question goes for a toss. Moving on to the first step, we find order n, which is fairly straightforward given that we already know how to find n. In the case of a Butterworth filter, we take these values, we put them here, and we get n to be 1.91. So no prizes for guessing. The order is going to be 2. The order is 2 because it's rounded off. Coming to step 3, where we calculate the minor and major axis. We have epsilon by this. Epsilon is basically the denominator in the formula of, not um, epsilon is, you'll have to pardon my poor handwriting here, cos h inverse root over whatever is here. This is epsilon. Let me change the color of my pen, please. This is epsilon, and this is lambda, and whatever is here. So we need this epsilon. We already know that value given that we have calculated the order of the filter. With this, we find out that epsilon is equal to 1. Similarly, we use this epsilon to find mu, which is 2.414. And as I said, it's all a game of formulae, pardon me. 2.414 goes here, we get A and we get B. We are leaving this in the terms of pi because we can either let it be or they shall eventually end up getting cancelled, as we shall see forward. Step 4, one of the more essential steps. I mean, all steps are pretty essential, but because this helps us get the denominator of the transfer function, I guess I called it more essential than the other steps, is the poles. The poles of a transfer function, of the poles of the filter, pardon me, given by sk is equal to a cos phi k plus jb sin phi k. If you remember what I told you before, k goes from 1 to n being 2 here because it's a second order filter. K goes from 1, 2, and that's about it. And this 5k here is given by pi by 2 plus 2k minus 1 by 2n pi, similarly k going from 1 to n, right? So we calculate phi 1 and phi 2. These values, I will change my pen color again. These values are given in radians. We convert these to degrees. It's pretty simple conversion rate. Pi is 180 degrees. So we get our values in degrees. We plug these values here. Sorry, this will go here. Pardon me, please. It's pretty late in the night when I'm recording this. And we get S1 and S2 to be minus 643.46 pi plus J1554 pi and minus 643.46 pi minus J154 pi respectively. Now that we have our pole values S1 and S2, we need a single denominator that will have S in it. And how we can get that is by taking this, putting it here, that is taking it from the RHS to the LHS. Similarly, in the case of S2, we take this entire value, this entire term, then this entire term, and we put that on the left hand side. And what that gives us is S plus 643.46 pi plus J1554 pi multiplied by S plus 643.46 pi minus J1554 pi. Now this looks kind of familiar, right? This looks somewhat familiar to elementary school algebra. What is that? A plus b whole square equal to a plus b into a minus b. The only difference here will be that our a value is not going to be one term, it's going to be a combined term. This will be our a, this will be our b, similarly this will be our a, and this will be our b. So now we have it, a plus b, a minus b, that gives us a square plus b square, and that's how we get our denominator. And since n is equal to 2 is even, we take s is equal to 0 and we divide it by 1 plus epsilon square. If you remember that condition which I had labeled as important earlier. If n is odd, we just take s is equal to 0, but in this case we have to divide that by 1 plus root over 1 plus epsilon square. So that makes the numerator of h of s, mind you, numerator of h of s to be 1414.38 square pi square. Therefore, putting the numerator back in the denominator spot and back where it belongs and putting the denominator back where it belongs, we get our final answer, which is our transfer function h of s. Thanks for watching. Do like, share and subscribe if this video helped you. Thank you.